Ahem. This podcast is brought to you by the AlmaMAC and Scientific Canada. It was recorded on the traditional territories shared between the Haudenosaunee and Anishinaabe nations. Enjoy.
What's going on, everybody? Thanks for tuning back to the AlmaMAC here on 93.3 CFMU, where we interview McMaster graduate students about their research. I would like to acknowledge that McMaster University is located on the traditional territories of the Haudenosaunee and the Mississaugas of the New Credit, and located within the lands of the Dish with One Spoon Wampum Agreement. So today we have another wonderful graduate student joining us today. Today we have Jennifer Williams, who is a third-year PhD candidate in the Department of Kinesiology under the Faculty of Science. How are things hanging today, Jennifer?
Doing great.
I'm happy you could join us. I know before we were talking about how you're coming in between your lab experiments here, so I'm happy your cells are cycling at this moment.
Absolutely. No, I'm thrilled to be here and to be able to share a little bit of my story and what I've been up to for the last, couple of years now.
Yeah. So why don't we kind of dive into that story if we can, and maybe we can start out kind of how the COVID-19 pandemic really caused you to be adaptable, maybe in ways that you never could have imagined. So,
absolutely.
Can you speak to that a little bit?
So I would say on the research side of things, I have been for several years now, about 6 years, a cardiovascular physiologist. So I've been doing research that looks at hearts and arteries in healthy folks and those with various clinical conditions. And we look at people at rest and then during exercise with various interventions. And so as you can imagine, with the COVID-19 pandemic, we really had to pivot our research. So I was studying prior to the pandemic. I was in a big trial where we were looking at the effects of different types of hormonal contraceptives, commonly known as birth control. And we were looking at how that affects arteries of folks. And, with the pandemic, we had to really shift that. We had to shut down our human research, and we've been shut down for about 15 months now. And in doing so, I realized that there was a need to shift my work. And actually, I've shifted into cell work. So I'm looking at the same hormones that are involved in contraceptives, but instead of looking in human arteries, I'm looking in human artery cells. And so it's kind of allowed me to look a little bit more mechanistically at the research to try to make a link between the human and some of the more cellular mechanisms. So it's been a fascinating ride. I can definitely speak to, the challenges, but also the successes that we've had along the way.
Yeah. And that's interesting that you talk about that pivot and now exploring this link between human and cell work. That must be really interesting. Before we dive into that, I'm curious if you can also speak to learning the new basic science techniques that you might have had to pick up, or if you had previous experience to that. I'm interested to know more about that.
A great question. So this is a while ago, but in my undergrad, I was in a life sciences degree. I had some experience, very basic experience in the wet lab, but largely was dealing in humans. So I was doing techniques that involved ultrasound, taking blood samples, those types of things. So really, the basic wet lab techniques that I had learned up until the point where I pivoted was, how to centrifuge down some blood and how to pipette. Very basic. Jumping into the cell lab, you learn how to grow up cells, how to make sure that they stay alive, which is more challenging than you can anticipate. I've learned how to quantify proteins, so different proteins in the cell. We use really cool things called probes, which allow us to look at the abundance of different metabolites. So we look at a metabolite called nitric oxide. It's found in the blood, and it helps our arteries dilate. And so we look at that in the cell to see how much nitric oxide there is. It's essentially this beautiful green probe. It almost looks like Christmas lights lighting up. So we look at that within the cell. So I've definitely learned a lot of techniques. I tell folks that it's almost like I'm on, a climb up Everest. I feel like I'm climbing this big mountain, learning all these techniques. So it's definitely been a very strong uphill learning curve. But I have been very well supported there's a cell lab that we're partnering with for this work, and they've been immensely supportive of really teaching me everything I know now.
Oh, that's wonderful to hear. And I think that's one of the real positives that have come out of this pandemic is just the immense collaboration between scientists, not just with regards to the pandemic, but even within our graduate labs itself. It's really nice to see.
Absolutely.
So Jennifer, if you kind of gave us a teaser of it with nitric oxide and these mechanistic links. If you can just give a large or a brief overview of what your research is about now during the pandemic.
Absolutely. So pre-pandemic, we were looking at, in arteries, when arteries have blood flow going through them, there's these cells called endothelial cells. And the endothelial cells release a vasodilator called nitric oxide. And essentially how those cells release that nitric oxide and dilate the artery is an indicator of cardiovascular disease risk. And so endothelial cells, nitric oxide, very, very important markers for future cardiovascular risk. And so in taking that into a cell model, we're still looking at essentially the same thing, but we're looking directly at the cells themselves instead of kind of a cursory marker in our ultrasound. So we're looking more directly at the cells. And so we look at a couple different things. The first would be we look at, the prevalence of nitric oxide. So how much nitric oxide is being produced by the cells at resting levels. And then when stimulated with this agent called acetylcholine. You probably know it from neurotransmitters in the brain and whatnot, but we use it to stimulate nitric oxide in our cells. And so essentially looking at this, we can kind of tell how much of this nitric oxide is being produced. We also look at different proteins and receptors that are involved in producing that nitric oxide. So a common one is endothelial nitric oxide synthase. It's essentially this protein it's an enzyme that's involved in creating nitric oxide. Outcomes that we're exploring. Having said that, what I'm most interested in is how different hormones change how much nitric oxide is being produced. And so I look at how endogenous, meaning within the body, so things like estrogen and progesterone, which are common sex hormones, affect the prevalence of nitric oxide. I also look at how these exogenous hormones, or what we take into the body, so through hormonal contraception, through hormone replacement therapy, different things like that, how that also affects nitric oxide. And we're thinking that different hormones may have different effects on nitric oxide based on what we're seeing at the human level. So now we're taking it down to the cell level and seeing if we're going to see similar things.
If I can pick up on that, when I was trying to read around this link of hormonal contraceptives and cardiovascular risk, to me, it kind of seems like a mixed bag. I was finding studies that suggested that hormonal contraceptives may increase cardiovascular risk, which is why some clinicians may screen women if they're smoking, if they have hypertension, diabetes. And another study suggested that they may actually decrease cardiovascular risk. So I'm wondering if you can speak to that link a little bit, or is that a gap that you're trying to fill with your research?
You've hit the nail on the head with that one. So it definitely is an area of research that's quite understudied. Women historically in cardiovascular research have been understudied. And so we're really trying to fill this gap. You're absolutely right that depending on the contraception that you're on, there may be a different risk profile that's associated. And so what I'm trying to fill a gap in is there's some early research coming out to suggest that with one of our main markers of cardiovascular risk, which is called vascular function, it's essentially how the artery responds to a specific test that we use in the lab, which has been linked to cardiovascular risk. Essentially, each of these contraceptives may have, beneficial effects or may actually have detrimental effects. And that may depend on their composition. So what types of hormones are in the contraception. So that may be why we're seeing, some contraception maybe putting us at risk, and some may be actually curiously benefiting our cardiovascular health. And so that's really the gap that I'm trying to understand is which contraception is posing a risk to women and which is not. And so looking at that in humans as well as in cell culture.
Mm-hmm. Yeah, it seems like since their introduction, since the 1960s, they've really come out with some variations. And especially, I think maybe they varied in their dosing with how much estrogen or progesterone is in these hormonal contraceptives, along with I guess the timing or the frequency at which women take them. So are you focusing on a particular, I guess, dosage or timing administration? Are you looking at the whole range of them?
Yeah, so right now we're looking predominantly at oral contraception because that is one of the most commonly used contraceptive methods in women. About 80% of those who are on contraception are using some variation of IUDs or patches or other methods. And so we're looking at two of the most common ones here in Canada. One is called a second generation pill, and the other is a third generation pill. And essentially generations are exactly as you described. Depending on when they were developed, they've kind of gone up in generations. So right now we're on fourth generation pills. And so really it's the makeup of the pill and the dosing level. So the level of estrogen in these pills has largely stayed the same. There's some slight differences, but it's really the progesterone that has changed over the years. And so I'm most interested in looking at how these different progestins regulate or change how our arteries function. And so, that's essentially what I'm looking at, mainly oral contraception, but we do have some other really neat projects where we're looking at emergency contraception as well. So emergency contraception is where you're given a large dose of only progesterone. It's a progestin called levonorgestrel. You're given a large, very, very large dose. And so we're interested in the acute effects or short-term effects of taking that pill as well. So lots of cool projects going on, but basically looking mainly at oral routes.
Fascinating. And Jennifer, if you can kind of walk me through, at least with your cell techniques, for instance, when you administer these hormonal contraceptives, what are you, measuring or looking for to see if it results in a positive cardiovascular outcome versus a negative cardiovascular outcome? What kind of things are you measuring and looking for?
Absolutely. So mainly we're looking at, so I mentioned before that we're looking at some of our protein markers. So these are proteins that regulate nitric oxide production. And then nitric oxide itself, we actually get to, it's kind of the coolest thing I've ever seen, where you can look at the cells themselves and you can see how they fluoresce. And the intensity of how they fluoresce is how much nitric oxide is in that cell. So that's really cool to see. I've never seen before. I've always heard of how nitric oxide is produced in the cells, but to actually see the gas in the cells being produced is pretty awesome. And so we're interested in looking at, so I dose the cells, meaning that I give them hormones at different levels that are the same levels that we would see physiologically. So essentially I've taken what, a woman might experience when she's on an oral contraceptive, like looking at her blood levels and taking a look at, what she's experiencing and putting that into the cells at physiological levels. And by doing that, I can then look at, the production of nitric oxide and look at some of these enzymes and receptors that are involved. It sounds all very, kind of more mechanistic. It's kind of complicated in that sense, but really what we're doing here is we're taking and trying to put into the cells to take a look at what's happening at that minute level.
And would you expect, if nitric oxide is something that dilates or opens up these arteries, would you expect that expect that if there's increased nitric oxide production or increased production of the enzyme that produces nitric oxide, is that a good outcome? Is that something that we're hoping for?
Exactly. Yeah. So if we're seeing that certain progesterone, certain estrogens are upregulating or increasing the amount of that beautiful green light, that nitric oxide that we're seeing, that would be a good indication. There are, of course, limitations to going from cells into humans and vice versa. So do want to say that, can't make broad conclusions based on the cell work, but at least it gives us some insight into when we take it back to humans, and we're starting to jump back into testing humans. We can, make those connections that if we're seeing, a drastic increase on one type of progestin, maybe we'll see the same in our human models. And if that's the case, then we can start to make some conclusions about cardiovascular risk. So that's the hope.
Fascinating. And Jennifer, I'm wondering if we can jump back to that, the human link there, because that's what you studied pre-pandemic. So you talked a little bit about the techniques that you use in the lab, but I'm curious, how do you measure cardiovascular outcomes in human participants?
Great question. So we use ultrasound techniques to look at what's called conduit arteries, or the big arteries of the body. So there's a common one. It's located in your arm. It's called the brachial artery. There's also another one that we look at in the leg, but it's less commonly studied. And we do this really cool test. We essentially put a cuff around the forearm, and we inflate that cuff above our systolic blood pressure levels. So we essentially occlude all blood. If you've ever slept on your arm funny and you kind of feel the pins and needles sensation, it's exactly like that. So we totally occlude, or not totally, but almost totally occlude blood flow. And when we release that cuff after a 5-minute period, it brings lots of blood flow through the arm. And we see this, what's called a hyperemic response, essentially lots of blood flow going down. And the degree that our artery dilates, which we can detect using ultrasound of the artery, the degree that that dilates is an indicator of cardiovascular risk. So there's been really neat studies that have connected that measure of vascular function to later cardiovascular disease events. So essentially, if you get a 1% decrease in that ability to dilate your artery, there is a 15% increase of cardiovascular disease risk. So knowing that, if we are seeing with different contraception that there may be differences, there may be an increase or a decrease depending on the type of contraception in that marker, that's a predictor then of later cardiovascular disease risk. So that's how we're making that link to this would be called an early risk factor.
That's fascinating. And again, kind of staying on that line. So for individuals that you bring into the lab, are you also measuring whether they were on any contraceptives, what kind, and maybe even for how long? Because if you can also speak, you're also interested in not just looking at the short-term effects, but the long-term effects as well. So if you can speak to that.
Absolutely. So when people come into our lab, we're interested in both knowing what type of contraception they're on, but also we're testing across what's called phases. And what I mean by phases is when someone is taking a placebo pill or a withdrawal pill. So they're essentially not taking estrogen, progesterone at that time. And then when they're in their active phase, which is when they're actively taking pills that have different estrogens and progesterones in them. So we're interested in looking at short-term, what I would call phasic effects. So that's just over a month, what's happening to your cardiovascular profile. So that's one part. The other part is how long you've been on your contraception for. So we have folks who've been on it for 6 months to as long as, I think the longest person I've tested is 12 years. So really a large spectrum there. And based on that, we can look at the relationship between how long you've been on a contraception and what your cardiovascular risk profile or your vascular function looks like. And there's been some really interesting studies, that very limited, but neat studies to find that the duration that you've been on certain contraception versus others seems to have an effect on your cardiovascular health with one contraceptive in particular. So I'm interested in exploring that relationship a bit further.
Oh, that's so interesting. Have you brought that relationship back at the cellular level? Like, is there a way to test short-term versus long-term outcomes in the lab?
Absolutely. So right now we're focusing on just that acute response. We're just looking at, if I dose the cells with these different hormones, what's happening to these outcomes? Having said that, of course, we could look at it long-term. So we're interested later, we might look at, dosing the cells for 7 days and looking at what happens kind of over a more chronic exposure. The cells grow pretty fast. So, 1 year in human years might be a lot less in terms of cell years. But yeah, we would be interested in, starting them off early, dosing them throughout their life course and seeing what happens at the end. But I think that's, the next stage of all this work.
Future directions.
Exactly.
And Jennifer, speaking of future directions, what do you hope are the implications of both your cellular and clinical work?
Basically, I got into this field recognizing that, women are generally understudied within cardiovascular health. And so I really happen an area I saw there was most need is in contraceptive research. There's very little when it comes to looking at cardiovascular health and predicting future health. So that was kind of the niche I wanted to fill. And so my hope from this research is that we'll be able to guide potentially some clinical outcomes, clinical directions, that when a woman goes to her physician and says, I want to be on a contraceptive, that there may be some discussion around cardiovascular health. Right now, we know a lot about, breast cancer risk and different cancers. We know the risk for major thrombosis or different types of like major cardiovascular events, but we don't really know if being on a contraceptive for a short or long period of time will help or hinder the cardiovascular system. So my hope is that, long term, we'll be able to make some clinical connections to this work. That's the pie in the sky, but that's the hope for long term. But for now, my hope is that this research will hopefully guide some work that's involved in, understanding the female vascular system.
Right. I was going to add that I think there may be some, when a woman goes to a doctor, perhaps asking for contraception, there may be some discussion regarding clotting. I think you mentioned as that might be the greatest risk factor, but here you want to take it a step further and kind of get a lay of the land of future cardiovascular risk.
Exactly. So if you knew now that being on one contraceptive over another might hinder or help your cardiovascular system, wouldn't that make you pause and think about, which one should I be on? Especially if, now women are on contraception for a lot longer than they used to be. And so I feel it's important for us to know if a woman's going to be on it for a decade, is that helping her heart and arteries or is it hindering it? And does that then help with making that decision for something that is so important?
Fascinating work, Jennifer. Okay. And Jennifer, for our listeners, I'm wondering if you can kind of speak to your journey. How did you get to where you are today?
It's a great question. So I started out like many folks getting into research. I didn't think that research was going to be a part of my future. I started out kind of by accident. I ended up sitting in a room where we were talking about different placement opportunities, research opportunities, just after class one day. And that's what got me started. I started in a research placement, did a thesis with a prof who was involved in kind of cardiovascular physiology and loved it from the minute I started. And that's really what's propelled me here. And I initially started by looking at how sugar affects the cardiovascular system. That's kind of how I started into this field. And so you might be wondering, like, how did I end up looking at hormones? And really how I developed that was I recognized in doing some of my master's research that despite about 40 years of study that had looked at how sugar impacts the cardiovascular system, nobody had looked at that effect in women only. And I felt like that was a really important thing to understand is how does sugar affect women's cardiovascular health. So I set out to do the first study that looked at exactly that. And I did it across different phases of the menstrual cycle. Mm-hmm. So phases when estrogen is low and a phase when estrogen is high. Because I was interested in looking at if estrogen helps, looking at the effect of sugar. Essentially, sugar impairs our cardiovascular health, which makes a lot of sense. And I thought that estrogen might help improve or help kind of regulate that.
Like buffer the impact.
Exactly. So essentially what we found was that women's hearts or women's arteries respond very similar to that of men's, that they're impaired with the effects of sugar, and estrogen doesn't help to rescue or blunt that effect, which was kind of neat to find out. And so that's really what propelled me into this whole area of research, because I recognized that, if one field has hasn't really studied, maybe there are some other fields that have done the same. So that's kind of how I got started with looking at how hormones affect our arteries.
Mm-hmm. Yeah, and I think it's really great that you're attempting to study a field that some may say has been neglected for some time. I think the stat that you gave earlier is that up to 80% of women will use hormonal contraceptives at some point in their life. So of course, this is affecting a large number of individuals. So I think that's wonderful that you're trying to examine that.
Absolutely.
So Jennifer, just in the last minute or two that we have left here, I wonder if you can speak to a few things that you enjoy doing outside of the academic setting.
Absolutely. So I think during the pandemic, I've really appreciated going out into nature, as I know many have here in Hamilton. I love your background because I think that really speaks to one of the most beautiful sites here. So I love to go hiking trails. I love to bike in and around Hamilton. Gardening has become a newfound love. surprisingly, and making good meals. I've learned how to cook during the pandemic, cook some proper good old fashioned meals. So, and the folks that I live with are a fan of my cooking, and learning how to do that over the last couple months. So,
that's awesome.
I've definitely appreciated that.
That's awesome to hear. I'm happy to hear about the gardening, because trust me, I tried to get into that too, but I got those little planters from Lowe's, and after 1.5 days, they are not holding up so well. So, any tips, or should I just throw them in my front yard and let the grass do its job?
Yeah, sometimes you just have to kind of put them in the ground and see what happens. Don't overwater. Sometimes that is actually the killer of plants, is overwatering rather than under. So a quick test is you can stick your pinky into the soil, and if it comes out, dry, water it. And if there's some soil on your finger, don't water it. That's actually the greatest killer of plants I've found.
Oh, okay.
Yeah. So I don't know if that's your situation, but, and sometimes it's good to, get them outside, get the sun on them. If they're sunny plants, that is. Yeah.
Okay. I got to try that then. Thank you, tip. Well, thank you so much, Jennifer, for coming on the show today and talking about your really fascinating and important research.
Thank you so much for having me. This is a blast.
Oh, I'm happy to hear that. And thank you to all of you who are listening every Thursday, 12 to 12:30, or wherever you're finding this podcast. It is appreciated. We will be back with another graduate student next week, but for now, take care. Bye, everyone.
Oh, hey, we got a couple extra minutes. Why don't we try something a little bit different? Here's an article I wrote for Massive Science. Enjoy.
Scientists capture the inner workings of the click beetle's explosive jumps. When you pull the film advance lever on an analog camera, you are loading a complicated system of springs and latches. With one smooth motion, you are not just advancing unexposed film across the body of the camera, you are providing the energy that will eventually release a cascade of action, ultimately opening and closing the mechanical eye as quickly as 1/1000th of a second. It's an impressive feat of engineering, but still far too slow to catch a click beetle's jump. Jumping like a click beetle requires an amazing amount of power different from human strength. We flex and contract muscles to perform work, which suits us just fine, since our muscles can efficiently generate sustained outputs of power. But click beetles don't need sustained power to perform their incredible jumps. Instead, click beetles lock, load, and fire themselves using spring latch systems similar to the inner workings of a mechanical camera. In normal situations, the click beetle skitters around like any other beetle on 6 tiny legs. But occasionally these beetles find themselves on their back with the ground hopelessly out of reach of their little legs. In such a situation, a click beetle may appear to squirm and flail at first, but soon enough it will begin to arch its back, pause, and then explode upwards with a loud click. This jump can launch a beetle with accelerations up to 300 times that of gravity, or 100 times larger than the acceleration felt by astronauts during a rocket launch. The jump gives them an opportunity to roll and somersault in the air, hopefully landing back on their feet. Though researchers have turned ultra-fast cameras on these powerful creatures, it's only recently that a team of researchers led by Amy A. Wissa, a professor of aerospace engineering at the University of Illinois at Urbana-Champaign, have been able to see the inner workings of the spring and latch system during an actual jump. They found an elegant internal spring system like a camera or catapult that unleashes its stored energy in the form of an ultra-fast and powerful jump. Imagine a click beetle divided into 2 halves, the head and the abdomen, which are connected by a hinge. The hinge mechanism also includes a peg and lip made of a stiff cuticle material. When the beetle bends backwards, the peg is pulled back across the lip where it can be latched, holding the beetle in its backbend. The beetle then contracts a softer, more elastic cuticle which acts against the latch, attempting to unbend itself. The resistance to this contraction is what loads the soft cuticle with elastic energy, much like stretching or compressing a spring. When the peg is finally released, it fires past the lip, releasing a huge amount of energy incredibly quickly. This sudden unbending of the hinge hurls the beetle into the air upwards of 20 body lengths high. Surprisingly, the beetles don't sustain any internal or external damage during the jump or landing. Of course, the beetle has a hard shell to protect it from sudden impacts, but how the beetle protects its insides from its powerful clicking was still somewhat of a mystery, until now. The researchers were able to see how the soft cuticle not only allows the beetle to store and release energy, but how it also dampens the explosive actions inside the beetle's body. The main difficulty researchers had in understanding the spring latch system of click beetles was actually observing their internal mechanics in real time. The latching and loading phases typically take a few tenths of a second, but the energy release phase is much faster. The researchers found that opening the latch and releasing the stored energy takes the beetle about 10 milliseconds, or a quarter of the time a single frame stays projected on a movie screen. High-speed cameras can work this fast, but they can't see through a beetle's shell. The challenge was to find a superfast imaging technique that could penetrate the shell and resolve the soft and springy materials, all while maintaining a high resolution to see the beetle's tiny parts. Wissa and her co-authors used an approach called synchrotron phase contrast X-ray imaging to overcome these complications. Normally, X-ray imaging measures how much light a material absorbs to tell you what's going on under the skin, but the X-rays also shift slightly when they pass through different materials. By looking at how much light is absorbed and how the X-rays have shifted, researchers can see hard stuff like bones, but also soft stuff, like the elastic cuticle inside the beetle that stores and releases energy during a click. And unlike the X-ray imaging you may be familiar with from visiting the dentist, these X-rays recorded images at up to 30,000 frames per second. Beetles usually perform their clicks while laying on their backs, so the researchers held their subjects still with a gentle clamp, allowing them to record multiple clicks without filling the air with springing beetles. This let them carefully track the moving parts inside a live beetle as it performed every stage of its click, from locking and loading to unleashing the stored energy. The results give us a better understanding of how the inner materials of the beetle can store and release so much energy so quickly, and demonstrates a non-invasive way to probe explosive processes within other tiny animals like pistol shrimp and trapjaw ants. The tricks these creatures use could inspire a new generation of small and super powerful insect-like robots capable of generating and sustaining high acceleration movements.